The ideal gas law shows us the relationship between all the different variables that we've seen, such as pressure, volume, the amount, and temperature. And the ideal gas law looks like this. It's PV equals nRT. And pressure is P, so this is the pressure. This is the volume. This is the amount, or moles. And T is for temperature, and this must be in Kelvin. All right, now there's an extra piece up here that we have not seen before in any of our gas law calculations, and this is a quantity right here, R. Now R is the gas law constant. What R does for us is it's a constant, and what it does is it cancels units for us so that we end up in the right units when we're done with our calculation. That's what R does. Now there's two flavors of R that we will use, and the first kind of R is 0.0821 liters, atmospheres, moles, Kelvin. And the second R that we're going to use is 62.4 liters, millimeters mercury for every mole Kelvin. Now if you look at these two R's, you will see that there's something different about them, and there's only one thing that's different about these R's, and that's the pressure units. We have atmospheres with this R, and we have millimeters mercury with this R. Now the way you're going to decide which R to use is you're going to look at the problem and see what the units are. What are the units for pressure? If you're using pressure units of liters and atmospheres and moles and Kelvin, then you're going to have to use that one. Or if you're using, say, millimeters mercury along with the other same units, you're going to have to use 62.4. So we let our units decide which R that we're going to pick. Also, when we look at R, this actually is a checklist of what the units should be in. Whenever you use this equation here, your units have to match up with whatever R is that you're using. So if you're using this R right here, the 0.0821, you must use liters. You must use atmospheres for your pressure, and you must use moles for your amount, and your temperature, of course, is always in Kelvin, no matter what gas law you're using. And so the same over here. You must be using liters, millimeters mercury, moles, and Kelvin for any gas law problem that uses this R. So we're going to let our units decide which R that we're going to use. Anytime we're using the ideal gas law equation, PV equals nRT, we are going to have to rearrange it. And what does that mean? It means whatever we're looking for is going to have to be by itself or isolated on one side. Let's say we were looking for pressure. Well, I would divide both sides by the volume, so I would have pressure equals nRT over V. Now what if I was looking for volume? Well, it's the same thing. I would have to divide both sides by P to get rid of the P and get it on the other side. So now if I want volume, it'd be nRT over the pressure. And what if I'm looking for the number of moles? Well, then I'd have to divide both sides by RT. And so that would be PV over RT gives me the number of moles. And finally, if I was looking for the temperature, well, I'd have to get temperature by itself. And so I'd divide both sides by NR, and so I get PV over NR equals the temperature. But at any rate, any time you're using the ideal gas law equation, start with PV equals nRT. Don't try to memorize these four relationships here. Don't try to memorize them. It's too much. What you do is you start with your ideal gas law equation and you just rearrange it to get whatever it is that you're looking for. If I'm looking for temperature, I got to divide both sides by NR and so forth. Just start with the ideal gas law and solve from there. Calculate the pressure in atmospheres of 2.00 moles O2 gas in a 10.0 liter container at 27 degrees Celsius. Now this problem has no pairs. In other words, there's only one pressure, there's only one volume, there's only one temperature. And so we have no pairs. The equation that we're going to use is the ideal gas law equation. PV equals nRT. Now the first thing we should do after we've identified the correct equation to use is go ahead and let's find what R is. R, the gas law constant, is going to be determined by the pressure units. Now if I look up here, I see the pressure units is in atmospheres, and therefore R, we look this up, is going to be 0.0821 liters atmospheres moles Kelvin. Now we're going to use our R to go back through our problem and make sure that every measured number up there is in the right units. Because when we use R, our pressure, our volume units need to be in liters. And we look up here, do we see liters? We sure do. There's liters right there. Our pressure units should be in atmospheres. It is in atmospheres up there, especially if we pick the R correctly by the pressure units. They should match up. And then we have moles. And do I have moles up here? I sure do. I got 2.00 mole oxygen gas. And finally, we have the temperature in Kelvin. I look for my temperature. 27 degrees Celsius is not in Kelvin, but we can put it into Kelvin by adding 273, which will give me 300 Kelvin for my temperature. So I've looked through with my gas law constant, and I've matched up all the units. Now all the units match up with R, including the temperature which is now in Kelvin. Now we have to rearrange our equation to calculate for pressures, because that's what we're trying to calculate. And so let's rearrange this equation. And so we say pressure is equal to N RT over V. And so we have the equation. We have our ideal gas law equation. We've rearranged it so that it's nRT over V. Now we can go ahead and plug in our numbers. And let's see, the N is the number of moles, and that's 2.00 mole. We have R, that's 0.0821 liters atmospheres moles Kelvin. And then we have the temperature, which we calculated, which is 300 Kelvin. And then that's all over the volume. The volume is 10.0 liters. And now we can put that in our calculator. Now, before we put this in my calculator, I would like to point out something, what I said before, which is our R makes our units cancel so that we have the right units when we're done. And if we look at this, at the units, you will see that moles cancels. And you will also see that liters cancels. And so does Kelvin. You see the Kelvin there cancels the Kelvin there. And so the unit that's left over is atmospheres. All the units canceled except for atmospheres, and that's what we're looking for, the pressure in atmosphere. So your R allows you to cancel all the units except for the one that you're looking for. Now we can go ahead and put this in our calculator. And let's see, we've got 2.00 times 0.0821 times 300 divided by 10.0. And I get 4.93 atmospheres. 4.93 atmospheres. What is the volume in liters of 4.00 mole methane gas at 18 degrees Celsius and 1.40 atmospheres? Now, the first thing I notice about this problem is that there are no pairs up here. No pairs. Which means that we're going to use the ideal gas law. PV equals nRT. Now, the first thing that I need to do with any gas law calculation is that I need to pick the R, and we pick our R based on the pressure units. And our pressures, the pressure is in atmospheres. Therefore, R, we look it up, R is 0.0821 liters, atmospheres, moles, Kelvin. Now, we will use our R, the units in our R, we'll use it to make sure that our units for our problem are in the right form. So first off, we'll look for liters, and do we have liters up here? Yep, that's what we're looking for for our volume. It's going to end up being in liters. Do we have the atmospheres? Yes, we have atmospheres there. We should have atmospheres if we picked our R right. Do we have the moles? Yes, we have moles right there. And do we have Kelvin? Let's find the temperature. No, it's not in Kelvin, but we can put it in Kelvin by adding 273, and that would be 291 Kelvin. So we've gone through our R, and we've used R to help us find and put our units in the right form. And so we have them all in the right form now. Now our next step is to solve for whatever it is that we're looking for. We're looking for the volume. So we need to get volume by itself. So we'll divide both sides by P, and we will get volume is nRT over the pressure. So we have solved for volume. Now what we need to do is go ahead and put in our measured numbers and solve. And so we look up here and we find the number of moles is 4.00 mole methane. And R, well, we've decided we're going to use 0.0821 liters atmospheres, moles Kelvin. And our temperature, well, we just calculated it was 291 Kelvin. And we're going to divide all this by the pressure. What was the pressure? There it is 1.40 atm. Now our units cancel, of course, because we're using the correct R. We should check. Moles cancel, Kelvin cancels, and we're left with liters, and atmospheres cancel there. And so there you go. R cancels everything except for the volume, which is what we're looking for, which is liters. And so now let's go ahead and put this in our calculator. This step, by the way, is, I'm just doing this for illustration purposes. It's generally, you don't end up using it. If you pick your R correctly and you do go through and make sure your units match up, then R will cancel the units. It's not something that I always check. So it's 4.00 times 0.0821 times 291 divided by 1.4. And I get 68.3 liters. 68.3 liters. A 10.0 gram sample of krypton has a temperature of 25 degrees Celsius at 575 millimeters mercury. What is the volume in milliliters? Well, I see that we have no pairs up here, and so the equation that I'm going to use is going to be the ideal law equation, ideal gas law equation. And here it is, PV equals nRT. And as always, when we use our ideal gas law equation, the first thing we need to do is find our R, and we do that by looking at the pressure units, and you look it up, and we see that R is 62.4 liters, millimeters mercury for every mole Kelvin. And we use our R units to help us make sure that we have the right units before we plug in to our formula. And so we see liters, and I look for the volume, and it says, well, we're looking for the volume. What is the volume? And we're going to have to take that liters we're going to get as a result and turn it into milliliters. Now we also look up here and we see millimeters mercury. We have millimeters mercury. If we picked our R out correctly, we would have the right pressure units. We look down here and we see moles. I don't see moles, I see grams. Anytime I see grams, I know I'm going to need the molar mass, and so we need the molar mass of krypton, and krypton's molar mass is krypton's molar mass is 83.8 grams per mole. 83.8 grams krypton for every mole krypton, and we're going to use our molar mass of krypton to find the number of moles, which is what we need here. And so let's go ahead and do that. And so I'm going to find the number of moles of krypton. We have 10.00 grams krypton, and a mole of krypton is 83.8 grams krypton. Once again, always making sure that we use our molar mass as a conversion factor. I had to flip it over to get the grams krypton to match up the grams krypton. And let's go ahead and put that in our calculator. And we have 10.0 divided by 83.8, and I get 0.119 mole krypton. So now we have our moles. We're letting our gas constant guide the choice of our units. So we got our liters, we have our millimeters mercury, and we now have our moles. And do we have the Kelvin? No, we have 25 degrees Celsius, but that's easy to fix as well. And so 25 degrees Celsius plus 273 is 298 Kelvin. So now we have all the units in the correct form. We have liters, we have millimeters mercury, we have moles, which we just found, and we have the degrees Kelvin, which we just found. Now we're ready to take our ideal gas law equation and rearrange it, solving for volume. So divide both sides by pressure. Now we have the equation that we're going to use. We've already verified that all our units are in the correct form, so let's go ahead and plug them in. And so the volume is going to be equal to the number of moles. That's 0.119 mole. We have our gas law constant, 62.4 liters, millimeters mercury, moles Kelvin. We have our temperature, which is 298 Kelvin. And we're going to divide by the pressure, which was 575 millimeters mercury. And we'll get our answer in liters. And so let's take our numbers. 0.119 times 62.4 times 298 divided by 575 is 3.848 liters. Make that a better looking L for you. There it is. Now we need our answer in milliliters because that's what the problem says. What is the volume in milliliters? There are 1,000 milliliters to a liter. So let's go ahead and convert this into milliliters. So we've got 3.848 liters, and there are 1,000 milliliters for every liter. I know I have this set up right because liters cancel and I'm left with milliliters, and so this would be 3,848 milliliters. And with significant figures, we have 3 significant figures for all of our numbers, and so that would be 3,850 milliliters. 3 sig figs, we go 1, 2, 3. Look one more over, that's 5 or greater, so we're going to round up that 4 and replace that 8 with a placeholder 0. We're going to round up that 4 to a 5 and replace that 8 with a 0 as a placeholder 0. What is the pressure in atmospheres of 16.8 grams fluorine gas in a 454 milliliter container at 21 degrees Celsius? This is an ideal gas problem because we don't have any pairs up there. We just have a single value for temperature, we have a single value for volume, and we have grams up there as well. So the equation that we're going to use is going to be PV equals nRT. And the first thing that we're going to have to do is pick our R. Now we pick our R based on the units, the pressure units. And I see ATM up here, or atmosphere, so my R is going to be 0.0821 liters, atmospheres, moles, Kelvin. Now our R tells us what units that we have to use in our calculation. And so I'm going to use my R and the units to make sure that everything is in the right form, in the right units. And so I look here first and I see liters, and my problem is in milliliters. Well, that's not liters. So I need to turn that into liters. There's 1,000 milliliters for every liter. And so let's go ahead and get that volume first. Let's see, 454 milliliters, and there are 1,000 milliliters for every liter, and that's 0.454 liters. 0.454 liters. Okay, well, I have my volume, and I check and see that we have atmospheres. We do have atmospheres. If you choose your R right, the pressure unit should always match up. And I see right here I have moles. Well, I don't see moles anywhere up here, but I do see grams. And anytime I see grams, I know that I'm going to have to get whatever's in grams is going to have to be in moles at some point in any problem we do. And so we have grams fluorine, and I need to turn that grams fluorine into moles fluorine, which is what is in our gas law constant. And so I'm going to need the formula weight for fluorine. And so a fluorine, if we look at our periodic table, is 19.0. There's two of them. And so that's 38.0 grams fluorine for every mole fluorine. Now that I have my molar mass, I can go ahead and get our moles from our grams fluorine. And so that is just like this. And we're going to say 16.8 grams fluorine, and a mole of fluorine is 38.0 grams fluorine. And now I just need to put that in my calculator to get the moles of fluorine. So we have 16.8 divided by 38.0, and I get 0.442. Mole fluorine. 0.442 mole fluorine. Now I have the moles, and now I look over here and I need to find my temperature, and it must be in Kelvin. Well, my temperature is 21 degrees Celsius. That's certainly not in Kelvin, but we can fix that, and that would be 21 plus 273, which equals 294 Kelvin. So I have looked through my R, and I've got the volumes, the pressures, the moles, and the kelvins. And if I don't have it in the problem exactly like it is in the gas law constant, well, I went ahead and did the conversion and put it into the proper units. Now that we have everything in the proper units, and we have all our data, all our measured numbers, it's time to rearrange our ideal gas law equation. What are we looking for? We are looking for the pressure. And so I'm going to divide both sides by volume to get pressure by itself. And so we have P equals nRT over V. There's the problem that we're going to use with our numbers that we pulled from the problem. So let's go ahead and put in our numbers and see what we get. And so the number of moles we calculated, it's right over here, is 0.442. That's what N is, 0.422 mole. Our R, well, we figured that out based on the pressure units. And our temperature, well, there it is. We had to add 273 to get our 294 Kelvin. And then finally, we're going to divide the whole thing by the volume. And the volume, well, we had to turn it into liters, and there it is, 0.454 liters. And now we can put this in our calculator. And so what do we got here? We got 0.422 times 0.0821 times 294 Kelvin divided by 0.454. And I get 22.4 atmospheres.